it's math and beats. And what we're going to take a look at in this video is combine all the ideas we know about derivatives thus far and what they tell us about functions, and go ahead and graph some functions. So that's what I'm talking about. Our goal is to use everything we know so far about derivatives so that we can draw a very accurate graph of a function. Now, before we do, just kind of give a brief general strategy. Like, not everything that we do when graphing functions is based strictly on derivatives, right? There's limits involved, continuity, domain and range, asymptotes. There's a lot of stuff. So kind of just like recap here what kind of things that we're going to be looking for. So we're wanting to graph some functions, say f of x. Okay, that's the goal. Then let's look at the first few things here. There's more after this, but we should understand what the domain is, right? What's the domain of the function, or which interval are we actually focused on here, right? Is it the entire domain of the function? Is it some sub-interval of where the function is defined, right? We should understand where this function is being graphed. Also, we're going to use derivatives to find some behaviors of the function, so might as well go ahead and find what the first derivative is and the second derivative is, assuming, of course, they exist. From there, we can identify all critical points of the function. Perhaps these are some locations of local extrema. And then, from there, once we've found these derivatives, the first and second derivative, go ahead and find where this function on all intervals is increasing, decreasing, concave up, concave down. That'll give us a lot of information about the function. And so, we want to go ahead and perform sign analysis on both the first derivative and the second derivative. Moreover, we can use the first and second derivative tests accompanied with, of course, sign analysis on the second derivative to figure out where all the local extrema are of the function itself and any possible inflection points. The function may or may not have asymptotes, but if it does, we want to figure out if there are any horizontal or vertical asymptotes. And if there's no horizontal asymptotes, in general, what's the long-run behavior of the function? We could also go ahead and find all the intercepts, all the horizontal and vertical intercepts. And when we combine all of this information, we should be able to draw a pretty beautiful graph of the function, piecing together everything here. So there's a lot of stuff, right? But, just go piece by piece and find all the relevant information and plot this function, whatever it is that we're dealing with. So that's a general strategy, right? It's just a place to start. Lots of things to look for. Now, we're going to start by looking at an example here in which, instead of just being given a function and its rule and then dissecting everything, let's start by looking at an example for which we don't know what the function is, but it's going to have a graph such that a whole bunch of different conditions are met simultaneously, and we piece together all this simultaneous information to draw a very nice graph of the function. So let's first look at that. Just can we, you imagine if we found this information on some other function, we do the same thing, but here we're given the information. So here's a few first things that have to be true about this function that we're about to graph. There's more to come, by the way. 5 different conditions to start with here. In part A, it says that the limit as x goes to negative infinity of the function is 3. So because that's true, it tells us there's a horizontal asymptote, if you will, of y is equal to 3 as x goes to negative infinity. So in the negative x direction, the function tends to the output value of 3. In part B, similar, but in this case, the limit as x goes to infinity of the function is equal to 1. So again, that's again telling us that we have a horizontal asymptote, but this time it's going to be y is equal to 1, and it's in the positive direction. As x goes to infinity, the function tends to the output value of 1. There's a couple other limit statements given to us here. In part C, the limit as x goes to 5 from the left of the function is infinity. So that is telling us there's a vertical asymptote at x is equal to 5. Vertical asymptote here, if you will. What is it? X is equal to 5. And moreover, as x goes to 5 from the left, the function y, or f of x, is going to positive infinity, right? Now, there might be other things going on to the right, but just because of that, we have a vertical asymptote. You can see there's a part F. There's more to come. In part D, as x goes to 5 from the right, the function goes to negative infinity. So again, we have the same conclusion as the previous part. Part C, there's a vertical asymptote at x is equal to 5. But in this case, as x goes to 5 from the right, the function is going to negative infinity. So it has opposite behaviors on the left and right hand sides of 5 for this vertical asymptote. So we got a couple horizontal asymptotes, the long run behavior of the function. We got this vertical asymptote at x is equal to 5 with opposite behaviors on both sides of 5. And then in parts E and F, we are told information about the derivative itself, f prime of x here. In part E, the function's derivative is positive on this interval, negative 1 to 2, union 4 to 5, union 5 to infinity. So what is that telling us? Well, f is increasing here on this interval, right? So in each one of those intervals, the function will be increasing. Whereas in part F, the derivative of this function is negative on the interval negative infinity to negative 1, union 2 to 4. So this is where the function is decreasing. Right? So we're just kind of dissecting piece by piece to remind us of all these different things that matter. Now in this statement, state G, there's a whole bunch of values. The value of the function at 0, the value of the function at 4, the value of the function at 6, and the value of the function at 2. These 4 locations are all equal to 0 here. So in fact, that's information given to us about the horizontal intercepts, in this case, the x-intercepts. So all information about x-intercepts, or horizontal intercepts in general, right? We have that, but then we also have these 3 different values of the derivative, f prime of negative 1, f prime of 2, and f prime of 4, all also equal to 0. So at this place, we have horizontal tangent lines at these locations, right? And so there may or may not be local extrema at those locations. Then some information about the second derivative. The second derivative is positive on this interval negative 3 to 1 to 3 to 5. That means the function f is concave up. But in part I, the second derivative of the function is negative on this other interval, negative infinity to negative 3, union with 1 to 3, union with 5 to infinity. This is where the function f is concave down, right? So we got a whole bunch of stuff here. Vertical asymptotes, horizontal asymptotes, intervals of increasing and decreasing, the horizontal intercept locations, locations of horizontal tangent lines, and also intervals of concavity. And then finally, there's some conditions here, there's some random conditions. The value of the function at negative 1 is negative 1, and the value of the function at 2 is 2. And so these are just random points, right? So -1 comma -1 has to be on the graph, and 2 comma 2 comma +2 also has to be on the graph. So then you say, okay, once you go piece by piece, what each specific thing tells us about the graph of the function, we want to take all this information and start piecing it together on the actual graph. So below is this plane. Here's the plane. That's where we're going to draw all this information, okay? So I'm going to kind of go back and forth between the conditions above that we just discussed about and this plane and piece together all this stuff to form what we should be doing, and that is drawing a beautiful graph of this function. All right, I think a good place to start is actually with the ordered pairs. We know some stuff, right, in part G here, okay? We got a bunch of ordered pairs, specifically at the x locations of 0, 4, 6, and -2. We know at those locations that the function is going to be having a horizontal intercept. So we go to those locations. -2 comma 0, boom, x-intercept. 0 comma 0, boom, x-intercept. 4 comma 0, there it is, x-intercept. And at 6 comma 0, x-intercept. So there's some intercepts. We also know in parts J and K some other ordered pairs, right? Specifically the ordered pair -1 comma -1, right there. That has to be on the graph. And 2 comma 2 has to be on the graph. So I'm kind of just going through these points first to start piecing together some particular locations for which the function is defined. And so far, that's where we're at. So we're done with those. We did those, except, of course, in part G, we have to go back and remember there's these locations for which the derivative is 0. So eventually we'll have to piece that together with other information about where the function is increasing and decreasing and whatnot. However, right now, we can go to these locations and we could start thinking, okay, we have to have some type of horizontal tangent line there. Now notice that x is -1, that's right there, right? So we know at that location, it seems to be already indicating there might be a local min there, but we'll see. But I draw a little line right through it, just to indicate, like, right there, they got to have a horizontal tangent line. At x is 2, same thing, right? Horizontal tangent line. We know that one. Draw a little line there just to help us remember. And then at 4, also horizontal tangent line. So now we can really say, okay, we've taken care of part G there. What else? Maybe let's save the increasing, decreasing, and concavity for last. Let's tackle the asymptotes now. A and B here, parts A and B, we have a horizontal asymptote of y is 3 as x goes to -infinity, and we have a horizontal asymptote of y is equal to 1 as x goes to infinity. So why not go ahead and draw in those horizontal asymptotes? We know as x goes to -infinity, this function should be tending to the line I'm trying to draw right there, that scattered line, y is equal to 3. And as x goes to +infinity, it should be tending to this line, y is equal to 1 here. So we can go ahead and take care of that long run behavior in parts A and parts B. In part C and D is the behavior of the vertical asymptote at the location of x is equal to 5. So we know there's a location here, x is 5, for which we're going to have a vertical asymptote, right? So I'm going to go ahead and just draw that in, that vertical asymptote, and might as well just label it while we're at it, right? The more labels, the better, more information. Now, what about the behavior there? Well, as x goes to 5 from the left, the function goes to infinity. So I go back to my graph and say as x goes to 5 from the left, this function has to be going straight up. So I'm going to leave that little vertical line there to help me remember that the function's got to be going up to infinity as x goes to 5 from the left. So we did part C, right, but that's done too. In part D here, as x goes to 5 from the right, the function is going to -infinity. So as I approach phi from the right, the function has to be going down to negative infinity. So that little line down there going to negative infinity, if you will help us remember the behavior on the left and right sides of the vertical asymptote x is equal to 5. So we did part D. There's a lot of stuff here. The only last piece of the puzzle is parts E, F, H, and I. And these are all parts of information for which tells us where the function is increasing or decreasing, and also concave up and concave down. So we want to start putting that all together so that we can figure out what the behavior is, right? So let's just start, I know there's a lot to see here, but maybe if I circle that, and circle that, and circle this, and circle this, okay? We cross that one out so we don't get distracted. Let's just start from negative infinity and work our way from left to right. What's going on? Well, we can see in part F that the function should be decreasing from negative infinity to negative 1. However, in part I, the function is concave down from negative infinity to negative 3. So decreasing and concave down from negative infinity to negative 3. What's that going to look like? Well, wherever we are at negative 3, we don't necessarily know where we are, but let's just kind of say, I don't know, we're somewhere here, baby. We know that the function has to be tending to y is 3 as x goes to negative infinity. And then we need to be decreasing and concave down. So it's got to look something like that, right? Decreasing and concave down, and I drew it kind of higher up there, right? Because as x goes to negative infinity, the function should be tending to 3. But moreover, the function's going to eventually have to pass through this point, negative 2 comma 0. Now, as I get to negative 3, the concavity changes, right? We took care of that concavity there. The concavity is going to change to concave up from negative 3 to positive 1. However, remember, from negative infinity to negative 1, the function is still decreasing. So from this location in which I'm changing concavity at x is equal to negative 3, the function is now going to change to concave up, but continue to decrease until negative 1. So there's this location where we change from concave down to concave up. And at that point, we can see that our picture should look something like that, right? Decreasing and concave up from negative 3 to negative 1. The function continues to be concave up from part H there until positive 1. However, we've taken care of that interval now, and we are now going to be increasing from negative 1 to 2. So in fact, from negative 1 to 1, combining parts E and H, we're going to be concave up and increasing from negative 1 to positive 1. So, got to turn to concave up, increasing here. I have to pass through that point, right? I got to keep increasing like so until positive 1. Concave up and increasing. I've now taken care of the negative 3 to 1 part here in my concave up condition. I then turn to concave down from 1 to 3. And remember, I'm still going to be increasing all the way up to x is equal to 2. So I'm going to change my concavity here, continue to increase, and I hit that horizontal tangent line that we already talked about that was at 2. X is equal to 2. I've now taken care of my negative 1 to 2 increasing part. My function's now going to change to decreasing from 2 to 4, and I'm going to continue to be concave down from 1 to 3. So at 3, I'm going to become concave down, but I'm going to now start decreasing, concave down, and now I will change to concave up at x is equal to 3. At 3, we're concave up again, but we're still decreasing, remember, until the number 4 in part F up there. So decreasing, but now concave up, something like that. So I've now taken care of my decreasing part. I then increase from 4 to 5, and I'm going to be concave up still there. And we know at x is 5, as we approach 5 from the left, the function has to go to infinity because there's that vertical asymptotic behavior, and thus my graph is going to look something like that, concave up and increasing there. I continue to be concave down after 5, right? I'm done with part H. I'm now going to be concave down from 5 to infinity. And in fact, we took care of the 4 to 5 interval for increasing. 5 to infinity, we must be increasing. And we know the behavior here, right? As we approach x is 5 from the left, there's that vertical asymptote going towards negative infinity. And I've got to be concave down and increasing. And thus, my function must look something like so as it approaches the horizontal asymptote y is equal to 1 as x goes to infinity. So that's a lot of stuff, right? There's a lot of stuff. However, this stuff is all stuff that was given to us in this particular problem. And piecing everything together, piece by piece, we can come up with the graph of this function here, which is the graph of this function f of x. So we do have one more example to look like. And in this other example, what we're going to look at is we're not going to be given any information. We're just going to be given a function and say, graph it. So we're going to have to find the information above. But I think this example is nice to start with because given the conditions, it's nice to have the strategy and see how we piece together all the different parts to produce a pretty accurate, right, relatively accurate graph here. So let's now take another look at something similar to this, another example. But this time, like I was saying, is we're just given the function. Here's the function. F of x is 2 minus 2, x to the 2/3 plus x to the 4/3. We'd like to graph this function using our calculus techniques, similar to all that information that we saw in the last problem. And that's it. We don't have any other information. And so one of the first things that we'd like to do is just figure out, well, if we're going to graph this function, what's the domain of the function? The domain of the function here, we'll notice we have all odd root functions, right? We have a 2/3 power and a 4/3 power going on the powers of the x's, and hence the domain of this function will be all real numbers x, or negative infinity to infinity. Note also, f of 0 is 2. Immediately we can get the vertical intercept, or in this case, say the y-intercept of the function, which is 0, 2. That belongs to the graph, right? So those are some immediate things that we can figure out right away. Now we think, are there any x-intercepts? Well, we'd have to figure out, in this case, where the function is equal to 0. Now, that's the same, of course, as setting 2 minus 2x to the 2/3 plus an x to the 4/3 equal to 0. And that might not seem like a trivial thing to be able to solve. However, if we look closely, this is actually a quadratic type of function here, in that if I let, say, the variable u equal x to the 2/3, then it follows that u squared is equal to x to the 4/3. And so if I instead write this as f of u, which would be 2 minus 2u plus u squared, or equivalently u squared minus 2u plus 2, then it becomes quadratic, right? That's part of the reason why we call it a quadratic type. And we could try to solve that quadratic equation to figure out if there are any x-intercepts. So let's do that. If that's going to be true, then u will be, using the quadratic formula, a positive 2 plus or minus square root of negative 2 squared minus 4 times 1 times a positive 2 all over 2a. Now notice, if you compute that radicand there, you get 2 plus or minus square root of 4 minus 8, which is just a negative 4. I left that a there. Over 2. So that negative radicand tells us that there are no x-intercepts. Because if there were, then there would be some solutions here for u, but there are not. So this function never crosses the x-axis, and that's okay. So far we got the domain is all real numbers. This function has a y-intercept at 0, 2, and there are no x-intercepts. So now let's start playing games with the derivative now, right? We got to figure out what this function's increasing and decreasing and concave up and concave down. So let's go ahead and find the first derivative. F prime of x here is going to be, well, it's just power rules involved. So it's going to be a negative 4/3 x to the negative 1/3, differentiating the term, the negative 2x to the 2/3 term, plus a 4/3 x to the 1/3 power. So power rule, power rule. Now notice I can rewrite this. I can factor out the common factor of negative 4/3 x to the negative 1/3, and what I'm left with is a 1 minus an x to the 2/3 power. So why am I doing that? Well, because we'd like to also at this time find any critical numbers or critical points that there might be. Notice that f prime of 0 is undefined, right? Because of that x to the negative 1/3 in front. We'd be dividing by 0, and hence x equals 0 is a critical point, right? And moreover, notice that 1 minus x to the 2/3, if we set that equal to 0, then that's the same thing as saying x to the 2/3 is equal to 1, or equivalently, x can be plus or minus 1. So these are also both critical points. X is 1 and x is negative 1. Notice that x is 0 is a type 2, meaning that the derivative is undefined there, and then x is 1 and negative 1 are both type 1. So we'll keep track of these. Now, we might as well, while we're at it, go and do some sign analysis on the first derivative. So here is sign chart. Here's f prime. Here's x. Let's figure out what's going on. We know at negative 1 and at 1, this function's derivative is 0. And at 0, I'll just write a u for undefined. Now, if you pick a giant negative number and plug it in, you get a negative times a negative times a negative, which is negative. That's right. So to the left of negative 1 is negative. Plug in, say, a number between negative 1 and 0, say negative 1/2. We get a positive number. Of course, you can verify this. I'm kind of just skimming it a little, but plug it in. This is the result. If you pick a number between 0 and 1, say x is 1/2, you're going to get a negative number. And if x is larger than 1, some gigantically large number, then you're going to get a positive number. And so that's the sign analysis on the derivative. And it tells us some stuff, right? It tells us that f is increasing on the interval, well, where this derivative is positive, and that'd be from negative 1 to 0, and also from 1 to infinity. We can also say that the function is decreasing on the interval where this function's derivative is negative. So negative infinity to negative 1, union with 0 to 1. Also notice that based on the sign changes that we have, there must be a local maximum value at x is 0. And remember, the domain of this function is all real numbers. And even though the derivative is undefined there, we still do indeed have a local max for this reason. So we'll have to figure out what's going on with the concavity to conclude exactly the behavior there. But we know that there will be a local max at x is 0. And if you go ahead and, of course, plug in 0 into the function like we already found right up here, that ended up being 2 as an output. So at that y-intercept, we're going to have a local max. So local max at 0, 2. We also have some local min values here. And those occur at both x is 1 and at -1. And in fact, if you go ahead and plug in 1 and -1 into the function right here, what you will find is that it produces the output of 1. So the locations of -1, 1 and 1, 1 are going to be local mins for this function. So we pieced together a rather good amount of information so far, but yet we still have to deal with the whole concavity situation. So let's go ahead and find f double prime of x. So remember, f of x, its derivative is right up there. So if I then differentiate that to get my second derivative, I will get a positive 4/9 x to the now -4/3 power, and then plus a 4/9 times x to the -2/3 power. Power rule, power rule. Again, I can factor out some stuff. Let's factor out a 4/9 x to the -4/3 power. And what I'm left with is a 1 plus an x to the +2/3 power. That's useful because, again, we'd like to figure out when this second derivative is either 0 or undefined, because there can be possible inflection points and possible changes in concavity. Notice that if x is 0, second derivative is undefined, right? F double prime of 0 is undefined, but that should seem like so since the first derivative was also undefined at 0. If I go ahead and try to figure out where does f double prime of x equals 0, well, then I would have to set that equal to 1 plus x to the 2/3 power, but that's the same thing as saying where does x to the 2/3 equal -1, or equivalently, where does x equal plus or minus square root of -1 cubed, or just plus or minus square root of -1. So we're not dealing with complex numbers here. We're only dealing with real numbers, and hence what that tells us is f double prime of x is never 0. So there is this one location for which there is a possible change in concavity, but let's see whether or not we have an actual change in concavity at this location. Okay, so to do that, I'll again do sign analysis, but this time on f double prime. So at 0, we know our second derivative is undefined. If I pick a gigantically negative number and plug it into this second derivative, we will find that we have a negative times negative, which is a positive here. Positive times positive, which is positive. And in fact, if I plug in a gigantically large positive number, same thing. We get a positive. So there's no sign change in the second derivative at this possible location of x is equal to 0. And what that tells us is a couple things. One is there are no inflection points for this function, right? Because there are no changes in concavity, there are no changes in the sign of the second derivative. Moreover, it also tells us that the function itself is concave up, right? Pretty much everywhere except at 0. So it's concave up on the interval -infinity to 0, union with 0 to infinity. So now we're almost there. We're almost at the point where we can piece everything together. The only other thing to note is, are there any asymptotes? Well, clearly there are no vertical asymptotes, and that is because, well, the function's domain is all real numbers, and moreover, there's no location of x for which the function is going to become unbounded at the particular value of x. Are there any horizontal asymptotes? In fact, that's also there is no horizontal asymptotes here. Now, let's think about why that is true. Let's go back to the formula for the function right above. Here is my function right there. And we have combinations of cube roots, right? One is x to the 2/3 power, that term. And there's also an x to the 4/3 power. So as x becomes gigantically large in either the positive or the negative direction, then this function should be blowing up to infinity because of that term right there, right? It's the highest power, and that will tend to be positive in general as x gets gigantically positive in magnitude. So there are no horizontal asymptotes for that reason. However, we can conclude that as x goes to either infinity or negative infinity, the function itself is going to become unbounded in size, goes to infinity. So now's the time where we piece everything together, right? So let's do this all together now. I'm going to draw a nice little graph here, nice plane that we can work off. And I'll go ahead and label my axes while I'm at it. So several things, right? Remember, let's go all the way back. Domain's all real numbers, and we also have the y-intercept of 0, 2. So I'm going to go ahead and plot that here. Here's 1, here's 2. There's a point on the graph, right? We also concluded, if you recall, there are no x-intercepts, so I don't have to worry about putting any x-intercepts anywhere. Another thing, we figured out there's a local max at the point 0, 2, and we also figured out there's a local min at these 2 points, negative 1, 1, and 1, 1. So I might as well go and plot those 2 points. We already plotted 0, 2, but let's plot negative 1, 1, and 1, 1. So maybe if that's 1, maybe there's negative 1, there's 1. There's these special points right there where we know there are local minimum values. Local max at 0, 2, local mins at these 2 x locations, negative 1 and 1. And there's other stuff, right? We know we're concave up everywhere. Concave up for all real numbers, excluding x is 0. And in fact, remember at x is 0, not only is there a local max, but the function's derivative was undefined. So we think of concave up everywhere, and we have 2 local mins for which the function is smooth. So at the local mins, we could draw these little horizontal tangents, if you will, to remind us it's smooth there. There's no changes in concavity. There's no vertical asymptotes. There's no horizontal asymptotes. We know that as x gets large in both directions, the function is going to go to infinity like so. So now it's just a matter of, okay, we know it's concave up everywhere excluding at x is 0. So what's up with the increasing decreasing part? The function's going to be increasing from negative 1 to 0 and also 1 to infinity. And we have to be concave up. So from negative 1 to 0, concave up and increasing. From 1 to infinity, concave up and increasing. For the decreasing, right there, we're decreasing from negative infinity to negative 1 and also 0 to 1. So I got to be concave up everywhere. From negative infinity to negative 1 gives us a picture that looks something like so. And then also from 0 to 1, concave up decreasing, something like so. And as you can see, we have now plotted our function here. This is the graph of our function. F of x is equal to 2 minus 2, x to the 2/3 power, and plus an x to the 4/3 power. And how awesome is that? I know it took a long time, but there is a lot of things that we have to figure out using only our concepts of the first and second derivatives and some limits and values of the function that really allows us to draw a fairly accurate graph of the function itself. If we really wanted to, we could pick a whole bunch of other points and plot them down specifically to scale, but this is kind of the essence of what we're getting at when we talk about using the derivative to graph the function. And so hopefully those two pretty involved examples give you now a platform for which you are able to go and attempt some other types of graphing functions problems on your own. But this is the end of this video. And so, might as well just say it's math and beats. I'm out of here.